So we've talked about efficient representations, and we've talked about sufficient representations. But can we have both in the same package? Well, we can, and we call such a thing a basis. So we say v1 up to vm are a basis, or form a basis, for some subset V if the first condition is that V1 up to Vm are linearly independent, so they're efficient. The second condition is V1 up to Vm span V, so they're sufficient representers. So example, the canonical bases. For R3, say, the canonical basis is just the collection 1, 0, 0, 0, 1, 0, 0, 0, 1. So the collection of vectors where I pick off exactly one entry and one coordinate where I'm going to set it equal to 1, and the others are all zeros, and I take all those vectors. That's the canonical basis. How about another example? Well, let's show that this actually holds, right? So let's take all the linear combinations of 1, 0, 0, 0, 1, 0, 0, 0, 1. So this will be C1, 1, 0, 0 plus C2, 0, 1, 0 plus C3, 0, 0, 1, which will be equal to C1, C2, C3 for all real numbers, and that's equal to R3, so definitely we have spanning. So this should really be B. And then A, C1, 1, 0, 0 plus C2, 0, 1, 0 plus C3, 0, 0, 1 is equal to C1, C2, C3, and that's going to be equal to the 0 vector 0, 0, 0 if and only if the Ci's are equal to 0, and therefore we have linear independence. So that's very good. But there are some consequences of having a basis, or consequences to being a basis. So theorem, every basis of Rn has n vectors. Well, by the last theorem of the previous video, m, of course, has to be greater than or equal to n, right? So m, the number of vectors, has to be greater than or equal to n. On the other hand, OTOH, if m is strictly greater than n, then the rank of that A matrix, where I'll just write all the columns of this matrix, this rank is going to be strictly less than the number of columns of M. So these guys have to be linearly independent, or linearly dependent, rather. Thus, v1 up to vm linearly independent implies m is less than or equal to n. Since we have m is less than or equal to n and m is greater than or equal to n, we have m is equal to n, and we conclude the theorem. Now let's have it's nice to have a theorem that kind of collects together a bunch of different facts. So theorem, the following TFAE are equivalent. And this comes up enough that we actually want an acronym for it. V1 up to Vm in Rn are linearly independent. B, actually we want an n here. Right, so we're assuming that we have n vectors. V1 up to Vn span Rn. C, V1 up to Vn are a basis for Rn. And finally, the determinant of V1 up to Vn, this matrix where I put everything in the columns, does not equal to 0. So that's a nice characterization that ties together a bunch of different facts. As long as I have n vectors that live in Rn, this will always hold true. And because of these ideas, we now can set down exactly what we mean by the dimension of a space. So in particular, the dimension of V equal to the linear combinations of V up to Vm is M if we have that V1 up to Vm are linearly independent. So if I have a collection of m vectors that are linearly independent and span V, I'm going to say the dimension is M. So in this situation, and V may not be all of Rn, it may be just a subspace, right? So that's a little different from the theorem we have up here, but we can prove that. It can be shown. So fact, any basis of V has exactly m vectors.